Let's turn our attention now from thinking of these rational expressions as just expressions to thinking of them as functions. We can define a rational function in one of two ways. A rational function is just one whose expression is a rational expression. Or we can think in terms of function algebra. A rational function is one that can be found by taking the quotient of two polynomial functions. So if P and Q are polynomial functions, P over Q is a rational function. And the definition in terms of expressions, the definition in terms of function algebra, these are clearly the same definition, just two different ways of looking at it. So just to explore how rational functions work, let's see what happens when we try to evaluate one a few times. Here we have the rational function r of x is 2x squared minus 7x plus 5 over 3x squared minus 7x plus 10. So to find r of 4, I'm going to just take that expression and plug in 4 for x. So I have 2 times 4 squared minus 7 times 4 plus 5 over 3 times 4 squared minus 7 times 4 plus 10. And going through and plugging that in my numerator, I get 9. And in my denominator, I get 30. Depending on what we want to do next, we might leave it like that. We might cancel the common factor of 3. And give this as 3/10. Unless it says simplify, you don't have to simplify. So leaving it as 9/30 is fine, but we can also write it as 3/10. Let's see, let's take r of negative 2 next. In our numerator, we'll have 2 times negative 2 squared minus 7 times negative 2 plus 5. In our denominator, 3 times negative 2 squared minus 7 times negative 2 plus 10. Now be careful when you're trying to take negative 2 squared on the calculator that your negative 2 has to be in parentheses. Let's see what we get. In our numerator, we get 27. And in our denominator, we get 36. Again, we can leave it like that, or we can cancel a common factor of 9. And we can give this as 3/4. One more. We want to take r of 0. Can we evaluate a rational function at 0? Yeah, absolutely no problem with taking r of 0. We can't have 0 in the denominator of any fraction, but we can absolutely plug 0 in for x here. So when we do that, we get 2 times 0 squared minus 7 times 0 plus 5 over 3 times 0 squared minus 7 times 0 plus 10. And then our numerator, that works out to 5. Our denominator, that works out to 10. Again, we could leave it like that. Or we could cancel the common 5 and give that as a half. Of course, you can also just throw the entire rational expression into the calculator all at once. If you're going to do that, make sure when you enter everything on the calculator, you put your numerator and denominator into parentheses to make sure that you evaluate everything in the numerator, evaluate everything in the denominator, and then do the division. And usually if we're working with rational expressions, we're going to prefer our output as a fraction rather than as a decimal. Now, just like we did arithmetic to polynomials, we can do arithmetic to rational expressions. And as we study the arithmetic of rational expressions, we'll discover that we can add, subtract, multiply, and divide them and get another rational expression as the result. So the rational functions are closed under all four operations: addition, subtraction, multiplication, and division. That is, if we have two rational functions, their sum, difference, product, and quotient are also rational functions. So again, this is analogous to the integers and the rational numbers. The polynomials we could add, subtract, and multiply freely, but we usually can't divide. The rational expressions we can add, subtract, multiply, and divide. Just like with integers, we can add, subtract, multiply, but usually when we divide, we don't get an integer. With rational numbers, we can add, subtract, multiply, and divide. So the relationship between the polynomials and the rational functions is very much the same as the relationship between the integers and the rational numbers.